A convolutional neural network extracts millions of individual data points as it processes an image. To handle this volume, the network must aggressively condense the information it passes to the next layer. This process of streamlining data is called max pooling. The algorithm identifies the strongest signals, like the sharpest part of an edge or a high-contrast texture, and discards the weaker values surrounding them. This filtering process prioritizes the prominent features, separating the essential signals from the background noise. To see how this works, we can look at a small 4x4 grid representing one section of a detections map. The numbers inside represent the strength of features the network has already found. Some of these values are significantly higher than others. These are our strongest detections, and they are the only values we want to keep. Locating these maximums is the goal. To do it efficiently across the whole image, the network follows a specific set of mechanical rules. In many architectures, like tiny VGG, this extraction relies on two specific settings, a 2x2 kernel and a stride of 2. The 2x2 kernel defines our search area. It starts by looking at the top left quadrant of our input grid. The algorithm identifies the single highest value in that box and isolates it into the first slot of a new, smaller output grid. A stride of 2 tells the kernel to shift exactly 2 spaces right, covering a fresh set of pixels with no overlap. The network repeats the rule, extracting the highest value from this new quadrant and placing it into the next available output slot. The scan continues on to the next row. By moving in these fixed 2-pixel jumps, the network evaluates every part of the input with no redundant calculations. As the kernel moves to the final quadrant, try to identify which of these 4 numbers will be selected for the output. The highest number in this group is the only one the network carries forward. We started with 16 values and reduced them to just 4. By keeping only the maximums, the network has successfully discarded 75% of the data while retaining the core features. This reduction forces the network to become less concerned with the exact location of a feature. Because the resolution is lower, the model cannot memorize the hyper-specific layout of its training images. This creates spatial invariance. If a feature, like the tip of an ear, shifts slightly within a region, the max pooled output remains the same, allowing the network to recognize the object regardless of small movements. Choosing the maximum value is essential for maintaining sharp details. While averaging those numbers would produce a muted mid-range value, max pooling preserves the most intense signal. By focusing on the what instead of the exact where, the model becomes resilient to distortions and less likely to overfit on the specific noise of a single dataset. In summary, max pooling extracts the highest value in a region using a kernel and stride. This reduces the total data by 75% and helps the network generalize what it learns. This highly compressed data is now ready for the final stages of the network, where these consolidated features are flattened for classification. The process ensures that only the most significant evidence reaches the final layers, resulting in a model that is both computationally efficient and more robust.